This is going to be audience participation talk, so you guys got to be ready. I guess I'm on California time, so I'm already like way up, ready to go. So my name is Chris, and I'm going to give the RISC-V instruction set architecture update. I'm giving this talk on behalf of Rick O'Connor, who's the executive director of the RISC-V Foundation. As for myself, I am completely unaffiliated. I am also not a RISC-V author, so I'm just a lowly grad student. Although I am advised by David Patterson and Chris Dosanovich, who are two of the 4 RISC-V authors, and I've been making RISC-V processors for about 5 or 6 years. So hopefully I can provide some level of informative, answers here. And also, I apologize, as a CPU guy, I'm going to give you information and updates filtered as a CPU guy. So, but also I think I'm in pretty good audience here. So quite a few things to cover. The first thing is that RISC-V was created at Berkeley. We've been using it for our research and our education for a couple of years now. However, as of last year, we created and incorporated the RISC-V Foundation. So our goal is to move RISC-V out of Berkeley and make it a real thing. Something that's a neutral development place. And we started this last year. There's now a board of directors that we just created, and we're just starting the long process of moving the tools upstream. And another way that things move from academia out into industry is students graduate. And so the lead RISC-V devs have graduated Berkeley, and they're now at a startup called Sci-5. But we also have new students that come on board, and we're still doing our research, and we have that on GitHub. So for the foundation, this is a nonprofit consortium chartered to standardize, protect, and promote the free and open RISC-V instruction set architecture for use in all computing devices. And Rick has been pretty busy in the last year. He has over 40 founding companies and organizations that have joined on to RISC-V. So this is a pretty impressive cross-section of technology. You have old industry titans. You have startups that are still in stealth mode. You have academic researchers. You have non-profit industry labs, and you have across all the a lot of the continents here. You have both the U.S. You have in Europe. You have China, India. A lot of people are putting their weight, their money, and their engineers behind RISC-V. There is a board of directors. Cross section of industry. Also, my 2 advisors, Krista and Dave, are on it. So that's how I get information to give this talk. One of the functions of the foundation is to have twice-a-year workshops that have been very well attended. We keep selling out, and we keep trying to make them bigger and bigger. So this past summer was at MIT in Cambridge, Massachusetts, and we had 250 people from 60 companies and 40 universities. So these are a lot of fun, and hopefully I'll see you guys in 2 months at Google headquarters in Mountain View, California. So the thing that I want to really kind of say about the foundation is that we're just really just now getting it going, and even though RISC-V has been around for a couple years, this is really the inflection point where you're starting to get company engineers starting to put their efforts into this. So this is really it'll be really interesting to see where RISC-V goes, because this really is just the beginning. Okay, so now into more of the nitty-gritty details of RISC-V. So we have 4 ISA extensions, 4 base instruction set architectures that are under the RISC-V umbrella. And then within that, we have extensions. Some of them we've frozen, and some are just placeholders, and some haven't even made the slide yet. So there's a wide variety of progress here. In terms of the memory model, this is one of these things that we're going to have to hammer out as we move to ratify the extensions in the foundation. So currently it's very relaxed. I think it's inspired by the Alpha ISA, and you have to use a lot of fences to enforce the ordering that you actually care about. And we're working hard to put together really a formally verified memory model, and figure out what is the memory model, formally verify, and then maybe what should the memory model be. And to give you an idea of kind of what our goal here is we want to make it really easy to implement the C11, C++11 memory model. And we have to kind of figure out exactly what that means. And by easy, I mean so that way the compiler guy can emit the right instructions, and hopefully it's not hard for the CPU to implement that. So as an example, we have to specify the acquire release semantics on the AMOs. to deliver the memory model that's expected. But one thing I can say is at a minimum, we will have to strengthen up and enforce the ordering of loads to the same address on a single thread have to be in order. So that's not currently specified by the spec. So this is still a work in progress.
Hey Chris, real quick,
Yeah.
can you talk about what's involved with formally verifying a memory model?
I have no idea.
Okay, all right. Sounds hard.
This is, the great thing about something that's open source is you have all sorts of research groups and industry groups that have a lot of experience. There's a lot of PhDs that have gone into memory models and consistency models and such. So I'm glad that we're having this kind of support behind RISC-V. So there's the compressed instruction set. I think we've talked about this in the past, but we're pretty happy with it. We think it's about finished, although we've not officially frozen it yet. And this is part of Andrew's PhD thesis work. So if you want some good bedtime reading, actually Andrew's thesis is a really good reading that I think this audience would really appreciate. And he goes into the details of how he designed the compressed ISA as well as how he designed RISC-V. In terms of the vector extension, unfortunately, there's nothing I can really discuss just yet. But hopefully we'll have a lot more details on the vector extension at the next RISC-V workshop. But what I will say is that our hope is that this is a vector extension that's scalable to all design points, and the CPU microarchitect can decide how he wants to trade off complexity for performance. And this is not something that's going to look like packed SIMD, AVX, MMX, SSE, and it's not going to try to look like a GPU. And if you finish with Andrew's thesis, then I recommend you go and read Krista's thesis, which is on vector microprocessors, and that'll give you kind of an idea of where we're kind of going with this extension. This covers kind of all sorts of the design points of vector processing, which is really, really cool. In terms of the privileged architecture, although we've not frozen this, there are quite a few OS ports that exist, like Linux and FreeBSD. Last year we had version 1.7, now we have version 1.9, and our tool chains, QEMU and Linux are all updated to 1.9. This is one of these hard things that you really just have to have more OS, development against more drivers. We're also just now on the mailing list starting to talk about hypervisors. And you also really need a platform spec, at least one example of a platform spec to make sure that you're really designing the proper reference privileged architecture. So these are the types of things that we need to get a lot of feedback on. So the RISC-V external debug specification. So this was, if the hardware works and you need to debug the software, this was created by Tim Newson at Sci-5, and so the idea is they will push this back to the RISC-V Foundation for consideration. So I know actually some of you guys have already been checking this out and you've already made the acknowledgments, but this is something that we hope is cheap and simple enough that all processors can use this for their debugging. And just to show an example of how this works, again, the goal here is that this is really simple and cheap. And you have a debug transport module. Unfortunately, with the resolutions, it doesn't work out. But the idea is, you have the DTM is going to write to some sort of debug RAM, and then the DTM can interrupt the core, and then the core jumps to a debug privilege mode, and he can start executing code out of the debug RAM. So basically, the debugger is just running short little programs on the core to get the core to do whatever it wants. So it can, read a register, it can read and write memory. So this gives you maximum flexibility. And also, this design it uses JTAG, but it's not tied to that. So the idea is you can come up with your own transport layer that's orthogonal to this specification. The other thing that has been recently added, which I think is really cool, is these high-performance monitor counters. So the idea is you want to measure things about what the CPU is actually doing. But it turns out that counters are really, really expensive, and so you need a software solution to be able to dynamically map which counters go to which events. So the idea is we're going to support nearly infinite events. You as a CPU guy can decide how many events you want to track, things like branch prediction or cache misses. And then we're going to support up to 29 physical counters. So the idea is you have 24 counters, and then you have 29 event selectors. So you can say that HPM number 3, I want it to increment whenever a branch misprediction occurs, something like that. And then there's 3 enable registers, so that way we can specify at different privilege modes, what you can have access to. So maybe the user level doesn't have access to all the counters to figure out what your crypto keys are or something. So this is what it looks like. And the reason why it's 29 and not 32 is because 3 of them are the cycle counter, instruction retired counter, and time counter. They also come along with the enable. So as a hypervisor, you could basically force the supervisor to trap if it tries to figure out how many instructions have been retired, and then the hypervisor can patch it up and lie to it. So this is a really cool, flexible way to figure out what your CPU is doing, or maybe block people from knowing what your CPU is doing, as it were. So for future progress, what has been going on at Berkeley and now at Sci5 is we'll continue to produce incremental proposals to the current user specs and the privilege specs. And we're going to start putting those on archive very soon, so that way there's like a change log, and also that it makes it a lot more clear that our proposals are just that. They're not RISC-V gospel, that they're on a separate location. As for the foundation, it's now starting to get its own working groups together. So nothing that I can really announce yet, but in 2 months we'll hopefully start hearing about what the foundation has put together for working groups to help strengthen and grow the ISA. In terms of software progress, like I said, we're starting to get things upstreamed. For things like BenUtil and GCC, previously I think we were blocked on lawyers, but now we may be good to go. And then for glibc and Linux, we're going to wait for the BenUtil stuff to get upstreamed. We're kind of receiving a bit of a mixed message here. Some are saying don't start it until you've frozen the privileged spec. Some are saying, no, you have to start upstreaming now so that way we can provide feedback on the privilege spec. So we'll have to figure out exactly what that story is. With QEMU, at least for our RISC-V branch, we have both user mode and system mode now, and Sagar is working on upstreaming the user mode. For LLVM, that's in Alex's wheelhouse, but my understanding is that you guys have started pushing patches upstream. I got a nod. Fedora just recently announced that they have disk images now, so you provide your bootloader and your kernel, and you can start leveraging their disk images. And then there's a lot of other talks that have happened at the RISC-V workshops, things like Core Boot and UFI and FreeBSD. So there's quite a bit of software that's been already using RISC-V. So with that, there's a huge ecosystem. This slide no longer even begins to cover it. There's a lot of hardware implementations. At Berkeley, we have the Rocket in-order core and the Boom out-of-order core. In terms of other people outside of Berkeley, there's the Pulp. We're going to hear about MRISC-V and such. So there's a lot of other things that I can't even begin to list. But I think with that, I'll take for any questions that you have on RISC-V.
Questions? Yeah. Right. You introduce yourself.
Hi, I'm Philip. When I wanted to give feedback or have a look at debug spec and stuff like that, would I join a working group, and how would I do that, and how does that work?
So that's a good question. We have an ISA dev mailing list. For the debug spec, you can go and download it, and I believe it explicitly says to send your feedback to Tim Newson. I don't know if he has a mailing list or anything of that sort. Okay, there's the debug mailing list? Yeah, okay, yeah. So at least for that, there is a mailing list for the debug spec. Yeah.
Hello, this is Stafford. About the timelines for GCC upstreaming or Linux, do you know when that would be done? Within 2016?
I have no idea. At least for a long time, we could go as fast as the lawyers would let us. There's copyright assignment challenges, and the problem is that we're paid as we're a public university, and we get money from the public and the taxpayer, and they don't like this idea of us assigning our copyright over to a third party. So those things get complicated. I think we may have resolved that. So then I don't know how fast the upstreaming will go. But we've been very quick and very fast about at least maintaining our own branch that's pretty up to date. I think we're on 6.1 GCC right now. But yeah, I don't know how fast that upstream is going to be.
Thank you.
Okay, yes, that's it for the RISC-V.